Yes, sir. We can see there.
Okay, so let
Yes.
me. Okay, so let's finish this series of lectures with examples of why phase transitions are so useful to study. So this is really a course for people. Yeah, this is the goal is really to give you an overview of where the kind of methods we studied can be used. So let's consider a very simple model of imitation effects. So the following model is modeling how votes. It's a very simple model of how can people can make very important decisions and without thinking too much. So it's a model where basically every voter is a binary variable. So it's like a spin in physics, takes value plus or minus one, corresponding to choice A or B. You have n voters. And so the way we're going to model these votes is the following. Every individual will be influenced by what we call a mean field. So it's and therefore the connection with mean field spin models, of course. You see that somehow the probability that at a given time, so it's a sequential dynamics, the voter I votes for the candidate A at time t, which in this language is a probability that SIT equal 1, will be proportional to exponential of the trend divided by a temperature. Okay, so what is the trend? The trend is just the average vote at time t. So basically what a voter does at any time is that it's sampling what people are doing, computing the average of what they're doing at that time, and this average will bias the vote towards one if this trend is positive, so more people vote for one. If instead this trend is negative, more people vote for minus one, then this probability will be less than 1/2, and the person will tend to vote for choice B. Okay, so very, very simple model. And you see, of course, that this trend is exactly like the magnetization in the Ising model. So perfect. So what is the temperature in this simple model? It plays the role of a kind of level of independence of individuals with respect to the dominating trend. You see that if the temperature is very high, this probability becomes essentially, this exponent becomes essentially zero. So the probability to vote one will be 1/2. It will be uniform choice for every voters. So it's a completely disordered voting process. Instead, if the temperature is low, then this exponent becomes very important, and every voter will tend to vote with very high probability the same as the average. Okay, so it will be strongly influenced by the others. And so if you simulate the system, it's very easy to implement in Python. So I did it, and you see what's the average vote. So you're computing this kind of average vote, the trend actually, which is like the magnetization, as a function of time when the system size is 10. Okay, and what you see for a given temperature is that you have large fluctuations. The system stays to close to +1 or -1 for a short amount of time. Then you have this abrupt changes like this, but it's very erratic. This is for small size. But now if you take the very same rule and you take n equal 100, so a bit bigger, you see something very different. You see a polarization effect. So you start from an average of 0, around half of the people vote for +1 and the other for -1. And then you have a polarization of all the people vote, like in this case, 80% of the people voting for the same candidate, -1, candidate B. And you don't see anymore the system escaping this state here. So you will stay there for a very long time, okay? And if you increase the size even more, you will stay there forever, essentially. So it's a very strong polarization effect of the voters. And this is what we call a spontaneous symmetry breaking of this system, in the sense that Here you have a symmetry between the +1 and -1 state, and you fluctuate from one to the other. And here you stick to one of the states, to everyone voting for the same candidate, and you will never escape this, even if the system is symmetric between the two, right? Between the two candidates, you could have randomly gone to the other candidate so that the average was closer to 1 instead of -1, and you would still stuck there forever. So it's the random fluctuation at the beginning of the dynamics that decide which state is chosen, but then you don't move from there anymore. So really more is different. You see a very qualitative difference between small and large system. And you can think of this as a very simple model of imitation in finance also. Instead of voters, you have buyers and sellers, and this kind of simple models, and of course much less simple models, are used to understand what are cracks, financial cracks in finance. So this is, for example, the value of the Dow Jones in the 80s. At some point, you've seen a big jump in the overall financial market, and this is a kind of phase transitions which is of the same nature as the simple model we just seen. Okay, so let me connect this to what we've studied in the course. This is the very same phenomenology as the ferromagnetic Ising model, right? So you remember we studied this model of binary spins, which are these variables that are interacting with all the others. So this is our factor graph, where every edge is an interaction with the others. And every of these nodes carry a binary variable, ±1. And you see that at high temperature, if you simulate this system, indeed, you see that the magnetization, which is the average direction of these arrows, fluctuates around 0. Okay, so this is the paramagnetic state that we defined. And instead, if you lower down the temperature, you see again a polarization. So you see that all the arrows will point in the same direction, and you will stick there. So this is the ferromagnetic state. Okay, so it's the exact same phenomenology as for these voters. Okay, and again, you can describe this in terms of free energy. So you see that, which again quantifies the competition between energy, therefore ordered configurations, and entropy, which favors more disordered interactions, which are more numerous. If you look at the free energy of this model as a function of the magnetization, which is, you see that for high temperature, it has a single minimum in 0. So this is this region at high temperature, it's the paramagnetic region. And if you lower down the temperature, the free energy becomes very flat there. And at some point below the so-called critical temperature, Tc, the free energy has two minima corresponding to the +1 state and -1 state. So this is the moment where the system pulls.
Your mic's off.
So for how long have I been talking without the mic? For a while, no?
No, 15 seconds.
15 seconds. That's weird.
10
okay,
seconds.
maybe. It's very strange. Okay, so if it happens again, please tell me. Thanks a lot. Perfect.
sir.
So thanks a lot. So so no, I was just saying that in the voters model, these arrows, the spins in the Ising model, of course, are the voters, and they feel the average trend. They try to do the same as all the other arrows. So this is the link with ferromagnetism. So let's see also the kind of phenomena appearing in animal behaviors. I really like this example. So if you go to Rome in Italy in the summer, you tend to observe these big flocks of birds, and they seem to follow a very interesting and rather coherent dynamics. They follow each other like this. And this has been studied a lot by statistical physicists in Rome in particular. And they identified also emergence of ordered phases, like in the ferromagnetic Ising model, where you go from paramagnetic to ferromagnetic. In this case, it's a bit richer. So this is a subfield of what we call active matter, in the sense that now every individual particle can take kind of informed decisions based on observing its neighbors. So these insects are kind of observing locally what is going on, and they're adapting their behavior according to their neighborhood. And you see in these systems very rich phase transitions and various phases. You have, for example, the swarming states, which are disordered states where basically every insect or birds fly away, fly randomly around a kind of center of mass. Then you have the polarized state, which is the equivalent of the ferromagnetic phase of the Ising model, where they kind of follow same common direction, and this is an ordered phase. And then you have the milling state, where they also move coherently, but kind of turn around center of mass. They kind of move as a circle like this. So there is no global movement. The center of mass is fixed here, while in the polarized state, the center of mass is moving. Okay, and this can also be described through the language of Ising type of models. Okay, these are very nice pictures. So this is the milling state in schools of fish, and these are kind of states which are polarized in birds. Okay. Let me also mention an interesting thing that people understood. Biological systems like birds and things like this, they tend to live very close, to place themselves naturally as a complex system as a whole, very close to phase transitions, in the sense that these kind of states are something in between disordered and ordered state. And the reason is that when a complex system lives close to a phase transition, the information like information propagation between one part of the system, one particle or one bird, to another one which is far away from it, is much more efficient. It happens much faster. So this is related to what we call criticality. So information processing becomes very, let's say, efficient and fast in critical systems living close to phase transitions, simply because close to phase transitions, somehow you can show that you have very long range dependencies and interactions between particles, calling particles generic entities in a complex system. You have very long range dependencies between particles which are even very far apart. Okay, and it implies a fast spreading of information. So okay, so let me move directly to computer science. So let's see some problems. Let's move away from physics to computer science and combinatorial optimization. Then we'll go towards communications and inference later, and then machine learning. So, but let me start with classical problems in computer science and see why the analysis of phase transitions and statistical physics is useful in this context. So the main, let's say, question one is interested in answering in a whole field, so overall in computer science, is the following one. Why are some problems easy to solve and some other problems are hard to solve? What makes a problem hard? And is there some generic features about problem that can we know in advance whether a problem is hard to solve? And by hard, I mean with an algorithm or not. In general, the answer is no. It's not clear in advance whether a problem is hard, but you you can approach these questions through statistical mechanics methods. So let me start with the grandpa, the father of all the problems in combinatorial optimization, in particular the birth. It's the analysis of this problem gave rise to what we call graph theory now, which is the problem called the 7 bridges from Königsberg. So Königsberg is a city here, just above Poland, which is nowadays called Kaliningrad. The name has changed, but at that time when graph theory was developed, it was named differently. And so in this city, there are three banks and an island in the middle, and you have bridges in between. Okay, and what people were trying to solve at that time, because it was a kind of game, is can you find a path that crosses all bridge a single time? So can you draw a line here that passes through all the bridge a single time? And so you have many possibilities to try. There are many places to start from and many choices to go everywhere. So you have a combinatorial number of possibilities. It's very many. So what you can try to answer the question is just try different ways. So people were trying for days and days to answer. But there was no systematic solution. We could not formally answer that question. So the only way was just trial and error. Okay, but Leonhard Euler, who was a Swiss mathematician, came out with a solution, and to do so, he developed graph theory. Do you still hear me? There is no problem? I hope so. Okay, now I have a doubt. Do you hear me?
Yes.
Yes, okay, perfect, thanks. Yes, okay, perfect. So the solution that Euler found came through abstracting a bit the problem. So what he has done is the following. He took the map and he associated every bank and the island to a node. So every piece of land which was disconnected from the others by due to the presence of water in between was associated with a node, a dot. And if two banks were connected by a bridge, then you was putting a bridge between these two nodes that he called an edge. Okay, and so he drew the first ever graph. Okay, which is an abstraction of this problem. And Euler found that he could prove that if more than two nodes have an odd number of edges, then there's no solution to the 7 bridge problem. So he provided an efficient algorithm to answer this game. You just had to count the degree of every node and to see if whether more than 2 had an odd number of edges. In this case, you knew that there was no way to pass through all the edges a single time. Okay. So this is an instance of an easy problem. You have a problem. Can we find a path crosses all bridges a single time? So this is called in computer science the problem of Eulerian path for obvious reason. And the algorithm is simple. Just check the number of edges of the nodes, and you compare with what Euler said. If the answer is no, there is an Eulerian path, and if it's yes, there is not an Eulerian path. And of course, checking this is just counting the degree of every node. It's an efficient algorithm in the sense that the number of operations you have to carry just grows with the number of nodes, or actually with the number of edges. Okay, so you have something more efficient than just trying all possibilities. Instead, the number of possibilities of such path, where you try all possible drawings, all possible paths in this graph, will grow exponentially with the number of nodes. Instead, this algorithm just grows with the number of edges, which is polynomial in the number of nodes. Okay, it's at worst n squared, where n is the number of nodes. So you have an efficient algorithm. So this is an easy problem. This is what we mean in computer science by easy. So yeah, just a quick remark. Now, two of these two bridge. This one has been changed to that location today, and this was one removed. So the problem has changed, the map has changed, and now there is an Eulerian path in the new problem in 2020. So now let's look at a slightly different version of the problem that looks very similar, but that is fundamentally different. It's called the Hamiltonian path problem, which asks the following: can we find a path that encounter each node a single time? Before it was every edge a single time. So you see, we slightly changed the question, but the problem is very different. So today, to the best of our knowledge, the best solution is just to try all possible paths. There is no efficient way to answer that question for a given graph other than just trying. Okay, and of course trying takes an exponential time because there are exponentially many ways to try to find path. Okay, and of course exponentials grow extremely fast. So even if you have a number of nodes which is 30, you would have to try a number of paths which is of the order of 10,000s of billions. So let's say if the number of nodes is around 50, if you want to try them all on a supercomputer, it would take more than the age of the universe. So this slight variation of the Eulerian problem, which is easily solvable, instead this variation is not solvable easily. Okay, so this is a hard problem. Okay, even if they look very similar. So this is what I meant by it's not easy to know in advance whether a problem is hard or not. Okay, that's why it's such a deep and important question also. So we have these two problems. One is very easy, the other is very hard. Okay, so in computer science, when a problem is easy like this and you can check, you can find solutions with a number of operations that scales polynomially with the number of nodes. In the graph formulation of the problem, it belongs to so-called P class, P for polynomial. These type of problems where we cannot find a better way than just trying all possibilities, we cannot be smart. These type of problems are called NP complete. So NP means non-polynomial in the sense that we don't know a polynomial procedure to find a solution. However, if I tell you this is a solution, you can check easily. It takes a very short amount of time to at least check that a solution is indeed a solution or not. And these are called complete. So not all hard problems are complete, but this Hamiltonian path problem is complete in the sense that you can prove using what we call reduction techniques. This is a whole field in theoretical computer science that somehow if you can give me an efficient algorithm to solve this problem, which we don't know, but you can at least prove that if such an algorithm exists, then with the same algorithm you could solve a very, very, very large class of other hard problems. So somehow they are all connected. They're just variations of a kind of big problem which encompasses them all. Okay. I haven't said it, but you can stop me anytime, of course, if there is any question. Yes, so if you solve one, you solve them all, and actually if someone can prove that, so if you can give me an algorithm that solves such a problem, you will become rich, because there is the Clay Institute in the USA that would give you $1 million, and they would also give you $1 million if you can prove that there is no efficient method to do so, to really prove that easy problems are, so the P problems are really a different class than the NP problems. So this is one of the most fundamental questions in computer science and also in statistical physics. But are there truly hard problems, or is it that we're just not smart enough? So today it is believed that there are truly hard problems, but there is no proof, because it's very hard to show that a problem is truly hard, because proving that something is easy is possible. You just need to exhibit an algorithm that solves the problem. Showing that something cannot be solved, how do you do that? So it means showing that all algorithms, including those that you do not know, cannot work, which is much harder, of course. Okay, so that's why this problem is an open problem. So now, how does it connect to statistical mechanics? So, of course, what I showed to you is that some problems are hard, like these NP-complete problems that can be hard in general, but of course you can generate instances of graphs and ask the same question, the same problem, and in this case it's very easy to solve. So let me draw this graph, and I ask you, can you find the path that passes through all the nodes a single time? And the answer is trivially yes, because there is only one path. So you see, of course, whether a problem is hard or not depend on the instance of the problem. So we have two extremes. We have some instances that can be very hard, some instances that can be very easy. So it probably means that there is a whole spectrum of hardness levels, if you want. And so the question is, can we understand what the spectrum is? And is it the case that there is a continuum of levels of hardness? Are there some problems very easy, then slightly less easy, medium easy, slightly hard, and very hard? Or is it that we go from very easy problems to very hard problem in a sharp way? These are two possible scenarios. And this is where statistical physics enters into play. So what StatPhys wants to understand, and what is basically define an ensemble of instances for a given problem, an ensembles of graphs, and try to understand for realizations of these random graphs whether problems are hard or not. Okay, so is a problem typically hard or typically easy? Okay, and so something must happen between the very easy problems and the very hard problems. Okay, and the transition between these two classes is usually sharp. It's not a kind of continuum of easy to hard. It's usually sharp. You go from very easy to very hard. Like in the spike-Wigner model, you remember in the phase diagram, the error of the best known algorithm was as bad as it can be as a function of the signal-to-noise ratio, which defines a kind of ensemble of problems. For every signal-to-noise ratio, you have a different problem. So the error was as bad as possible, and suddenly it was good. Okay, and it was optimal actually, and so the transition was sharp, and this is often what happens in this problem. And the transition between the two, of course, is a phase transition. Okay. So let me discuss another combinatorial optimization problem, which is called coloring, which is another instance of an NP-complete problem. So in the coloring problem, which is again one of the ancestors of graph theory, because it was a very important and concrete applied problem people were trying to solve a long time ago, is the following. I give you a map, and I ask you, can you color the map in a way that two countries that share a border have a different color? With only 3 or 4 or 5 colors. What's the minimal number of colors you need? Okay, and actually for maps like this, 4 colors are enough. So this is a theorem. It was conjectured a long time ago. Then the proof took more than 100 years to be obtained. So it looks like a simple statement once you try, but actually it's a very deep result. Only 4 colors are enough to color a map, and an algorithm to do it efficiently. Actually, it looks like once you know that 4 colors are enough, it should be easy to do, but it's not the case. It took additional 20 years to get an efficient algorithms to do it for general maps, of course. Okay, so again, you can write down this as a problem on a graph. You associate a node to every country, then you connect with an edge if they share a border, and you have your graph. And so the theorem tells that 4 colors are enough to color any planar graph. So a planar graph means a graph like this, where no edges cross, okay? And you can always map a planar graph onto an actual map, okay? So it's a graph that you can draw on a plane, on a sheet of paper, such that the edges do not cross, okay? And the properly colored graph is, of course, a choice of colors for this node such that adjacent nodes are of a different color. Okay. Now, let's make the problem more interesting. Okay, now we know what happens for planar graphs. Let's consider more generic classes of graphs, so more generic instances of the same problem. Okay, this is where the notion of ensemble of problems, of instances appear. And one way to define an ensemble of instances is by studying notions of random graphs. So we're going to associate a probability distribution to graphs, draw these graphs according to this probability distribution, and try to understand what is the hardness of coloring graphs depending on this probability distribution. Again, this probability distribution can be tuned by some control parameter, let's say the average degree of the nodes. And as a function of the average degree of the nodes, is the problem easy or hard is the graph easy or hard to color, okay, for an algorithm. So these are examples of random graphs, which are actually free colorable. So free colors are enough, but in general, you may need more colors, okay. And so now, using methods from statistical physics, like actually the replica method that we studied in this course, you can draw the phase diagram of the problem. Like we have drawn the phase diagram for the spike-Wigner model, you can do it for this combinatorial optimization problem in a very similar fashion. So here is the phase diagram. So the control parameter, which used to be the signal-to-noise ratio in our problem, is here played by the density of edges. So it's the number of edges is L. The number of nodes is n, and c is L over n. Okay. So the more you have edges in the graph, the bigger is the C. The more you have edges compared to the number of nodes, the bigger is C, up to a factor 2. Okay. So basically, what we do in these experiments is that we draw for any given value of C, you draw a very large number of random graphs with this average density of edges, where every node is kind of connected randomly to the others, such that the average degree is fixed to be C. Okay, and then you take your best algorithm and you try to solve the problem. Okay, and what will happen is the following: the fraction of random graphs drawn according to the distribution at fixed C that you can color will be 1, and then suddenly you have a drop, and then it goes to 0, and you see that this transition becomes more and more sharp as the system size increases. For 50 is in blue, for 100 is in red, it becomes more sharp. And with the replica method, you can predict that this becomes really a discontinuous transition at a precise value that matches the experiments, and so you have a discontinuous phase transition. So it means that you go from basically graphs that are easy to color. They can almost all of them can be colored in this region. So it's a colorable phase, to a non-colorable phase where almost all the graphs you cannot color them properly. You will always make mistakes. Okay. And now, if you test the performance of the best known algorithm to find these colorings, these are the dashed lines. So you track the computation on time this is some unit of time. You see when the system size is 50, you see some bump here around the transition, and then it goes down. And the bump becomes more and more pronounced as the system size increases. And actually, the bump here becomes exponentially pronounced in the number of operations you will need will grow exponentially with the number of nodes. And this is the onset of hardness. The problem is actually very hard to solve close to the transition, because this is the region where you have these long-range dependencies emerging between the nodes, in the sense that if you change the color of a single node for a graph with that average connectivity somewhere around here, it will have an influence on all the nodes in the graph. Essentially, you will have to basically flip a fraction of the nodes remain in the graph, even those that are very far away. You have these long-range dependencies that make the problem difficult. Instead, here, most of the nodes are disconnected or connected to few of them, so it's easy to find the colorings. And deep here, there, most nodes have a very high degree, so it's very easy to quickly say that you cannot color the node. Okay, but only close to the transition, the instances are truly hard due to these statistical dependencies. Okay. Okay. Yeah. So we're happy. This is really a phase transition. Okay. So you recognize this, like I told you, this phase diagram that we observed in the Spike-Wigner model. Here, where we had a statistically impossible inference regime, a hard regime, and then an easy regime for inference. Here we have something similar. We have an easy regime for colorings at low connectivities. We have a hard regime, and then we have a regime where it's impossible. The graphs, the probability to find a graph that is colorable is 0. So it's impossible. Okay. And this is the only region where free colorings exist. So around half of the graph are colorable and the other half no. But it's very hard to say so. Whether if I give you a graph with this average connectivity, it will take a very, very long time to or find the coloring or tell me, no, I've exhausted all possibilities and I could not find one. Okay. And of course, of course, not. This is far from obvious. The physics of these hard phases, this kind of phase diagrams are deeply connected to physics. Of course, you can think of this easy coloring region or the easy phase in inference problem as a kind of liquid phase, where basically the particles in a liquid are interacting just locally somehow. There is no long-range correlations with particles that are far apart in the liquid, and this induces. So you can think of. At the algorithmic level, this induces simplifications. Not having long-range correlations imply algorithmically easy problems. Close to the hard phase, the problem behaves more as a glass. Okay, and in a glass, you have these very long-range correlations between the molecules and the atoms in a glass. Okay. So now let's. Are there questions? I don't know if there were hands raised or any questions on the chat.
Any questions from audience?
Don't hesitate to stop me. So now I would like to show you additional examples. Yeah, sorry, there is one.
Myself, Tushar. I have one question.
Yes.
Actually, in that computer programming, I heard that means computer genocide means theorem genocide is applicable. Means in US, so many computer systems, supercomputer or whatever the latest quantum computing, the theorem genocide concept is there. Means if you organize one program in supercomputer or quantum computer with the help of physics theorem, then another theorems are genocide that program. So it's happen due to physical theorem. Means whatever the theorems available.
Can you repeat the concept you're saying? I'm not sure I hear properly. Just repeat the.
Actually, my question. Yes, my question is. Hello.
I'm listening.
Yes. My question is actually in computer system, and so whatever the supercomputer or whatever the new quantum theory, theoretical computers, there is the so many programming is going using the physical theorem, means that physical or statistical theorems using. So
Yeah.
there is the black side is also there. There is genocide, means if you design one program and another program are means oversighted that program. And so it's called genocide of the programs.
I've
Is
never
it
heard
happen?
about this. I never heard about
Okay.
this. But if you send me this on the chat, I will check. Then maybe I can answer your question later. I will check. I've never heard this term. I'm sorry.
Okay. Okay. Thank you.
Okay, so now let's go towards another field, which is actually the one we've been studying in this course, which is statistical inference. That is finding the hidden signal in the noise. Okay, so I think some of you know well communications, but let me redefine the problem and then explain the connection. So. How do phase transitions appear in communication? So communication problem is very simple. You have an emitter and a receiver that try to exchange some message, but of course the channel is noisy. So parts of the information that is transmitted is corrupted by noise, and so the problem is at the receiver side to find back this information. So one way, of course, I mean, the way to communicate and combat the noise, to try to beat the effect of the noise, is repetitions. It's adding redundancy in the message that is transmitted to fight against noise. So Claude Shannon, that we mentioned a lot in this lecture, is here and understood that there is a limit to communication. If there is not enough repetitions, redundancy in the bits that are transmitted, information will necessarily be lost. Okay, and if you want the ratio between the number of actual information bits you want to transmit and the number of bits that you need to send through the channel, including those repetitions, the ratio between these two is called the communication rate. Okay, and if this communication rate is too high, of course, information will be lost. So you have an emitter, a receiver, a noisy channel, but this information, yes, is corrupted by the noise. Okay, you have interferences. You will receive something which is noised. One model, for example, of noise is called the binary eraser channel. It's the simplest possible model where, with probability 1 minus p, the bits are perfectly transmitted. 0 goes to a 0, 1 to 1, and with probability p, a bit is erased. So at the receiver side, you receive nothing. So it randomly erases a fraction p of the bits. So the simplest way to communicate is really to literally just repeat the message. The simplest type of redundancy is truly repetition. So we call that a repetition code. You take your bits, let's say that 001 represents hello, and you just repeat it 3 times, okay? And indeed, when you are in a crowd or where you are at the phone and someone does not understand you, you simply repeat until the person gets the message. In this case, the rate is a third. Why? Because for every bit that you want to transmit, let's say the first 0, you had to repeat it 3 times. So you need to pay the price of sending 3 bits to communicate only 1 of information. So the rate is 1 over the redundancy, is a third. It's number of information bit divided by the number of transmitted ones. Okay. And what Shannon has proved in 1948 is that basically whatever code you're using to try to add redundancy in order to fight the noise, even if you're trying to use smarter things than just repeating, much smarter things, you cannot beat a certain communication rate. You cannot be beyond the communication rate. So this figure is telling you, assume that you allow yourself a certain error rate at the decoding side. So you allow yourself to lose, in average, let's say, one bit for every 10 to the 10 bits communicated. So it's a very small error, right? It's less than a billionth of the bit must be communicated correctly. So you put a line there and you ask, what is the maximum communication rate that I can attain? So what is essentially the minimal redundancy that I can allow myself to reach such an error? Shannon has proved that it's given by this curve here, by this wall. If you allow yourself 0 error, let's say 10, this is 0, then there is a maximum communication rate, okay? So there are two surprises here. And by the way, the communication, the repetition code we were talking about, where you repeat just 3 times, is there, okay? So the error will be of order 10 minus 2, of order 10 minus 3, of course, because in average you will lose 1 bit. If the probability of error of eraser is 10%, this repetition code with a third rate will attain a certain error which is there, okay, and a third is here. R3 is here. This is this line. This is the communication rate of a third. With a third rate, you can attain an error which is somewhere there, okay? So you can go from 10% of the bits erased to something like half of this, okay? And of course, the more you repeat, this is R5, where you repeat 5 times, the more you can decrease the probability of losing bits, the fraction of bits that will be erased, okay? And if you repeat infinitely many times, 61 times, you can make this error very, very, very small, of course, okay? So Shannon has shown that, first, perfect communication is possible, which is a surprise. It's the first surprise. Even if 10% of the bits that are transmitted will be erased, you can still find a way to communicate, to add redundancy in these bits, such that at the receiver side, you will make no error. Okay, so this is the first amazing fact. And the second amazing fact is that given a certain error rate, you cannot communicate more than at a certain rate. And this is called the Shannon capacity of the channel. And so this is really like a phase diagram in physics. So there is a region where communication is possible. This is a phase diagram as a function. It's error rate as a function of the communication rate. It's like a temperature and pressure in physics, if you want. These are two control parameters. And you have these two phases where you have a possible communication region and an impossible communication region. Okay. Perfect. And what happens in between is the phase transition. Perfect. So Shannon told us that whatever you do, and if you had access to the most advanced technology that will ever exist, you will never be able to communicate at a rate exceeding the capacity of the noisy channel. There is a fundamental phase transition that prevents you to do so. Okay? Perfect. So now let me discuss a very fascinating phenomenon which really links even more communication and signal processing with physics. Okay, and this phenomenon is called nucleation. So it goes like this. So the question is, so repetition codes, which are very stupid codes, you just repeat the bits, can attain this for a given error, you can attain this communication rate, which is pretty bad. It's very far from the fundamental limits that Shannon found. One remark is that Shannon has proven that this is the best you can do in terms of communication rate at a given error, but he never gave an algorithm to reach this performance, in the sense that you he didn't explain us how to code the information, how to properly add redundancy. This is the coding part. And secondly, given this unknown code, you would need at the receiver side an efficient decoding method. So given the observation of the noisy bits with the errors, how do you recover the original ones? This is the decoding problem. You need to solve both problems, and Shannon didn't. He just told us you cannot do better than this, which is quite amazing if you think about it. Being able to give a results for all algorithms without studying any is kind of quite amazing. So when there are kind of hard problems like this, nature has found a way to solve these hard problems in a sense. And this is called nucleation. And so this is more than an analogy. You will see that we use this in signal processing, in coding, everywhere. So this is super cool water. So if I click, so you see this is liquid water, which was actually below 0 degrees Celsius, much below. Let's say at minus 30 degrees Celsius, you put in the fridge for a long time. And if the water is sufficiently pure, what you would realize, quite amazingly, is that it will remain liquid in the fridge, even if it's below 0. But now if you perturb slightly this water, let's say with a punch, or if you put an impurity in it, you will see a kind of crystal appearing, ice, and then this ice will propagate like a wave, like this, starting from the nucleus, from the point where the perturbation occurred. You see really this wave here propagating. So the water crystallized suddenly in this kind of wave propagation, with this wave propagation. And the reason is that if you see, if you start, so this is again the free energy picture. Let's say you are above 0 degrees Celsius. So the minimum of the free energy is the liquid state. But if you slowly lower down the temperature, what will happen is that you will have this other minimum in the free energy that will appear until the equilibrium is the solid. But your system is kind of blocked in the liquid state because there is a barrier between these two states. There is, it would take quite some time if you want to jump around this barrier. Even if there are more, it's more favorable from the physical point of view, from the energetic and entropic perspective, to be solid at this temperature. It would take some help to reach that state here from the liquid one. Okay, so this is called super cool water. And the way nature solves this problem is by nucleation, in the sense that if there is any small perturbation in the system, mechanic or impurities, somehow it is enough to crystallize locally, and then once you crystallize locally, it propagates like this. It has to propagate, okay? And the reason this happens is that the system is has a kind of notion of dimensionality. It's not a mean field system like what we studied in the course. Like every variable in this water, every molecule only sees its local neighborhood. There is a notion of local neighborhood. While the problem that we studied in the course, like the spike-Wiener model, the variables have no neighborhood. If you draw the factor graph, as we did this morning for this problem, every variable interacts with all the other ones. There is no notion of local neighborhood, okay? And this prevents, in particular, this kind of nucleation to happen. So what you can do is to change the problem, and let's say now we go towards, go back to communication. We would like to exploit this nucleation phenomenon. And this is what modern error correcting codes are doing. It's called spatial coupling. So let me give you the idea. A way to code information is using what we call parity checks. There is a type of code which are called low density parity check codes, and they work in the following way. What you do is that the emitter that wants to send a message and the receiver, they kind of agree in advance on a big set of allowed sequences. These are the possible messages to transmit. And of course, if the number of sequences to transmit is big enough, you can map any words to one of these sequences. So you can transmit any information if you wish, if the alphabet is big enough. Okay. So the way to agree in advance on this sequence, to construct this dictionary, is by using what we call parity constraints or parity checks. So basically, you only allow sequences of bits such that some selected sums of these bits have to be an even number. Okay. So this you can represent this as a factor graph where the factors are connected to these nodes representing the bits to transmit. And if a factor is connected to some nodes, it must be that the sum of these nodes is an even number. So it allows to spread the information, to couple, to correlate these bits. So now imagine that you have constructed your code in a kind of chain like this. So you put the bits in line and you connect them with parity checks in this kind of structured manner. You see that the first bit, let's say, is always connected to an individual check. So it means that the first bit will always be a 0, okay? Because the sum of the neighbors of this guy must be a 0. There is only one, so it must be even, so it must be a 0. So even if it was erased from during communication, if you receive a question mark here, it was erased, you know in advance it was a 0 because you pre-agreed that it was a 0. So you already know this. But now that this bit has been reconstructed, due to this parity check there, this one can be reconstructed because you see it's connected to this one that you actually observed, plus this one that you just reconstructed. So it allows to reconstruct that additional bit. But this one is connected somehow to this one that was erased also. So it allows you to check that the sum of this one plus this one plus this one must be even. 1 plus 1 is 2. It's already even. So this must be a 0. And indeed it is, etc. So you see that you have a kind of decoding wave that happens starting from this kind of nucleus that we call also the seed, which is kind of the piece of information that you always agreed between the receiver and the decoder to send. It's always the same 0 that you send at the beginning. And it allows to decode starting from there in a kind of ordered fashion. Okay? And if you use this strategy, it works amazingly well. So here, I've used this strategy to decode bits representing an image. So it's not just bits, it's not just 0 and 1s. It corresponds instead to the values of gray pixels. So the value can be anything between 0 for black to let's say 200 for white, and any value in the between is a different level of gray. They are like bits, okay? And I've transmitted these bits through a noisy channel. What I received is what you see at the beginning. At the beginning, it's very noisy, and I'm trying to recover the image, okay? It's like a communication problem. And I've implemented a coding strategy of this sort. And if I order the pixels in the correct manner, I would see that there is a chain of dependencies between the bits there. And you see that the reconstruction error using an algorithm, it starts from the first bits which are reconstructed. This index is representing the bits in a kind of the right ordering. And you see a reconstruction wave that propagates from the seed and that propagates in the system, exactly like the seed of crystal propagates in this liquid water. It's the exact same phenomenon. So you can exploit this nucleation strategy that is present in nature as a way to achieve very high inference performance in signal processing or in communication. And if you do so in coding, you can actually design coding schemes that can reliably transmit information through a noisy channel up to the Shannon capacity. You can close that gap. So in the language of what we've done in the course, you remove the hard phase. Somehow it disappears. There is no more hard phase. Okay? Okay. I like this quote by Richard Feynman, who got the Nobel Prize in Physics in 1965. That connects. He understood directly, of course, that statistical mechanics, which is the mother of thermodynamics, or vice versa. Historically, thermodynamics appeared before, but statistical mechanics explains it. He understood the links with information theory. He said the science of thermodynamics began with an analysis by the great engineer Sadi Carnot of the problem of how to build the best and most efficient engine, and this constitutes one of the few famous cases in which engineering has contributed to fundamental physical theory. Another example that comes to my mind is the more recent analysis of information theory by Claude Shannon. These two analyses, incidentally, turn out to be closely related. And of course, they're actually two sides of the same coin. Statistical physics and information theory are very, very close cousins. I'm just checking if there's no question. I'm already beyond time. Do you want me to take additional 10 minutes to finish, or do you want me to finish now?
We can take 10 if you wish, yes.
Okay, so I will do so. Let me give another example of an interesting inference problem that I mentioned at the beginning of the course, which is community detection. So in this problem, you observe a graph. Okay, so a graph like this that looks random, but actually it's not random. There are communities hidden in it, in the sense that there are some groups of nodes which are more connected to each other than with the rest. Okay, so let's say this is the group of interactions of friendships between on Facebook. A node is connected to another one if they're friends on their network. And the task would be to infer back who is voting for who. Actually, these kind of techniques were used to bias the American elections during some years ago. There's been this scandal with Cambridge Analytica that was used by one of the two parties. I will not say which one, to try to bias people in voting in one or the other direction by targeting them. And so the first thing you need to understand is who is a priori voting which party. So this is this community detection problem. You have this is the data, this random noisy graph, and you want to infer the two communities, the blues and the red. Okay, and yeah. This is a hard problem, and another equivalent way to see the problem, by the way, it's exactly the same thing, is that I give you an adjacency matrix, which looks like this. This is the adjacency matrix of this graph. So there is a one, so rows and columns are indexing the nodes, and I put a one in this matrix if they are connected in the graph, okay? And so I give you a random permutation of this adjacency matrix, and you're trying to find what is the right permutations of the columns and rows, such that you exhibit this community structure. You see that nodes in this block are more connected together than they are connected with the other nodes, and these are the other group. So it's about finding the right permutation, and of course the number of permutations is even more than exponential. It's n factorial, where n is the number of nodes, so it's super exponential. Okay, so it's a very large number of possibilities to try. And the phase diagram of this community detection problem, as I told you at some point in the course, is actually the one of the Spike-Bigner model, if you define the things correctly. And what we called the signal-to-noise ratio in the Spike-Bigner model, the lambda, plays the role in the community detection problem of the relative probability of intra-community connection. So what do I mean by this? if lambda is 1, it means that a node in the graph that belongs to that is red has the same chance to be connected to another red node or to a blue node. And it means that the graph is completely random. Okay, there is no information about the communities. If instead this is different than 1, it means that you are more connected to, it's greater than 1, you are more connected to nodes in your group. So there is information in the graph. Okay, and the other parameter would be the fraction of nodes you reconstruct. And this phase diagram, which is the very same as we discussed in the spike-Wiener model, is understood for community detection through the analysis of the spike-Wiener model. And in particular, for example, to detect these communities, you can do a spectral algorithm, you can do PCA that we analyzed, and what you realize is that the top eigenvector of the adjacency matrix of the graph will give you information about these two communities. Some of the components will be more positive, some other more negative, and you can read the communities in this way, at least get an estimator for it, which is not perfect, but this top eigenvector contains information about the node states. Okay, but you can do something smarter, which is based on this AMP algorithm we discussed, the Bayesian algorithm. Okay, last example, machine learning. So the classical problem in machine learning is supervised learning. You have many others, but it's about learning from examples. So imagine that you have a big data set of labeled data. So you have images of dogs and cats, and they come with their label: dog, cat, etc. And you try to write down a program, an algorithm which is predictive. So you want that when fed with this data, it is able to correctly match these labels with these images. And in particular, you want that if you then feed your algorithm, your model with a new input, which does not come with a label, it will output the correct label. Okay? Yes, this is what I mean by this. Unlabeled data, you want it to spit out the correct answer. This is the supervised learning problem. So if I give you a certain number of data, you can use simple strategies to try to classify, to find a boundary decision. So this kind of two-dimensional space represents in reality the very high dimensional space of images, whose dimension is the number of pixels, so it's tens of thousands, but here I can only show you things in 2 dimensions, of course. But you should imagine all these images as a point living in a 10,000 dimensional space representing the images. And each of these points comes with a color, a label. So there are the dog points and the cat points. And you're trying to find a boundary decision between the two that separate the two classes. Okay, the more you have example, the more you can fine-tune this boundary decision, of course, until hopefully you find something which is predictive enough. Okay. Perfect. So this simple classifier is an example of the very simplest neural network you can think of. It's called the perceptron, or just a linear classifier. Basically, it takes as input an image, which are the values of the pixels. It will multiply this vector by a set of weights, and then it will apply a nonlinearity and spit a sign, dog or cat, plus or minus 1. So mathematically, you are taking an input, which is x, which you can vectorize this image if you want. You're taking the dot product with a vector, which represents these weights here, and then you're taking the sign. Okay. Perfect. And you can analyze the performance of such a model on a simple setting where, of course, the images are not dogs and cats, but you have some mathematical model for these images. They are kind of Gaussian vectors with there are 2 Gaussian clouds. Okay, it's like a Gaussian mixture, and you can compute using the replica method that we studied in the very same way. It was done in the 80s. The generalization performance of such a linear classifier. Okay, so once it has been trained, given a certain amount of training data, this is the control parameter, like the signal-to-noise ratio. You can track the order parameter, which is the generalization performance, the performance on unseen data that was not part of the training data. How good is the model at labeling unlabeled data? And what you see is that, again, you have a region where the optimal classifier like this has a bad generalization error, it's high, and then suddenly you have a sharp phase transition, and then it's 0. It means that you have found the perfect line that separates the two classes, okay? But you need enough data to do so. And this is really a phase transition again, okay? You see it's sharp, suddenly you can generalize perfectly. Now, if you try algorithms to find this this boundary, this classification, boundary, the true theta, you see that you need more data to find it. So efficient algorithms are these dots or this green line. And so the learning becomes easy only when you have more data that what information theory predicts. Information theory tells you that you should be able to perfectly generalize given that amount of data, but you don't know any algorithm able to do so. So this is a hard learning region, and then suddenly the learning becomes easy. Okay, so it's exactly the same picture. So that's it. I hope I convinced you that the methods that we've studied in this course can be used in plethora of other contexts, and all this can be unified actually through the language of information theory and statistical physics. And so I hope that it had triggered your interest enough so that you can take a look by yourself for applications of interest. And that's it. I will stop there.
Yeah.
So if there are any questions, I'm happy. If some of you are curious, I can send the slides, and I'm happy to share this.
Yes, sir, please. Huh? So, if we do not have any questions, I would like to express a vote of thanks, mentioning a big thanks to Dr. John Barbier, who has kindly accepted our proposal of doing Gyan course with us. Sir, we are so grateful that you attended and presented a different dimension of connecting computer science problems with information theory, statistical physics. We really never had this idea that we can also follow these frameworks. I myself has learned a lot, and then I
Thank
would
you.
like to mention, thank you, sir. I would like to mention the great support by our director, sir, Professor Vinod Kumar Kanodia, who has provided all the necessary support to conduct this Gyan course. And then I would like to mention Gyan National Coordinator, to sanctioned and accepted, who accepted our Gyan course grant. And as everyone knows, previously we were trying to have Professor John Barbier here with us so that we can connect and grow and learn and evolve with each other, but that couldn't be possible. So we would definitely be connecting with you, sir, again sometime to have you here in India so that we can learn. Then I would like to mention a gratitude to our Gyan coordinator from NIT Jalandhar, Dr. Vimal Bhardwaj, who has always guided us and supported us for any things to be done, for all the procedures and protocols to be done, how to be conducted, and I have always taken help. And then I would like to mention my another course coordinator, Dr. Deepti Kakkad, has always provided all the fruitful thoughts, ideas, and she is the only one who motivated me to do this course. I just went her telling her that I went ICTP. She told me you must propose a Gyan course. This is the kind of thing we can do, and it can really help our students. I was never introduced, so a big thanks to Dr. Deepti ma'am who introduced this course to me, and then another thanks to Dr. John Barbier who kindly accepted to do this Gyan course with us. Then I would like to mention our head of departments IT, Dr. Vijay Chahar, head of department EC, Dr. Ashish Raman, who have always provided their kindly support and infrastructure required to perform this entire course successfully. And definitely not least, not the last, the most important, I would like to mention all my participants who have attended, especially Dr. Julio, despite of having time lags from US. Dr. Julio has attended most of the sessions. Thank
Well
you,
done.
Dr. Julio. Then
Yeah,
I would
thank
like to
you. No, it
mention,
was very interesting, so it's worth it.
Thanks.
I remember we connected in Youth in High Dimension in ICTP Italy, right?
Yes.
So I
Yes.
hope, yes, we will be doing some more things great together. And then I would like to mention all the professors who have kindly accepted our course to join by looking at the importance and significance of the course, especially Professor Divya Bansal. Despite of her busy schedules, she decided to join us. Thank you, ma'am, for joining our course. Then I would like to mention Then I would like to mention Professor Shekhar Verma from Triple IT Allahabad and Dr. Arpita, Dr. Aarti, Dr. Tanu, Dr. Satnam, Dr. Amanpreet, all of my students, Fiza, Abhishek, Gagandeep, Amrit Raj, then Tushar, Sonali, I have no names. Some of them have been texting me. I couldn't attend this talk. I had some engagements. Then I have been sending them the notes and the required things to do. And so I believe that this course will really be fruitful to our postgrad and PhD students, and especially for research purposes. We would definitely be connecting with you for more queries, maybe about writing projects together, and then taking idea how can we connect our computer science problems with the concept of mean field theory of Bayesian inference. So this is another dimension you have introduced to us. So, with all
Thank
these
you very
words,
much.
I think words are not enough to express my thanks to you. So, if this to say anything,
No, I
Sir,
am.
we are very thankful.
Go
Sir, we are
ahead.
very thankful. We extend our heartful thanks to your invaluable insights. And your expertise has greatly enriched our understanding. It was truly privileged to learn from your user and keep stay in touch and continue this academic connection.
Okay, I am very. It
thank
was
you.
really a pleasure to give the course, and of course, I'm happy to engage in any discussion with the students, with anyone who wants to know more, and so don't hesitate to share your thoughts and send me a mails, and I will take the time to answer and clarify any things you would like to delve into a bit more.
Thanks a
Thanks a
lot.
lot. So goodbye,
Professor
everyone.
Divya, if you would like to say something.
Glad, I attended this course. It was definitely very mathematical, very intensive, very deep. Did take us a while, to get a feel out of it, but eventually, with the kind of applications which were explained and with a little more notes and searching here and there, finally, uh, we could really make it. And a lot of my PhD scholars were also attending from my lab, and my faculty was also attending. So it was like we had the entire research group was here. So the good thing is that we could discuss with each other, and now we are the entire team, 4 or 5 of us who have attended this course. So it was absolutely wonderful attending this course, and thank you to Jaspal and Dr. Deepti, for extending this opportunity to our institution, and thank you, Professor Reen. I hope that we'll also be able to collaborate on more projects and more research later.
Thanks very much. It's very kind.
Okay. Dr.
So
Julio, you would like to say a few words if. Okay, Dr. John Barber is saying something. Yes, sir, please.
no, I mean, I just want. No, I mean, no, I wanted to thank everyone for these very kind words, and I want to acknowledge that I know that it was intense, and also I want to express the fact that it was difficult for me to gauge also the level of everyone's. That there was a very big variance in backgrounds and knowledge. I've tried to find the right balance. It's not easy also because this field is extremely interdisciplinary and mixes language and concepts from very various fields. I hope you gain something out of it. And it was really nice for me to teach that. And again, 1 week was pretty short and dense for all this, but I hope that at least it have triggered some interest, and you have the right amount of seed, of nucleus in this field to start reading papers in your own. And any question in this, you can just send me, and I'm happy to Zoom to discuss anything, any question you may have. So thanks a lot. And thanks Jasper in
Thank you, sir.
particular, was my direct contact. Yeah.
Definitely, definitely. Dr. Julio, would you like to express how was your experience to be with us?
Oh,
Don't
I don't know. I'm a man of few words usually, but I think it was good. Like I said, it was very early in the morning, so it's a little bit more challenging, but it was very useful. A lot of information.
Thank you.
Thanks.
Definitely, next time we will keep US time zone also with us. We took care of Italy time zone. I think with Professor John, I will discuss with other time zones as well while proposing such courses in future so that we can have a common time to attend. So, any of my student, Fiza, Tushar, Gagandeep, if any of you would like to say a few words, or any participant would like to express,
I don't,
or
not
any other
everyone.
faculty member. Dr. Avni is there from my department. Dr. Vijay sir, HOD of our IT department, is also with us. Sir, would you like to say something, or ma'am, or anyone?
Don't feel obliged. Really, I think
Okay,
I got
okay,
enough
sir.
of.
Thank you, thank you. So I know you have a meeting after this, so I will not take much time. I thank you, everyone. So with this note, definitely we will stay in touch and we will grow together. So if we had any opportunity to connect, to work together, we would definitely be doing so. Thank you, sir.
Yes.
Thank you, everyone,
Yes.
for their
Very
Thank you.
participation.
Thank you.
Thank you,
It was a very
thank
informative.
you.
Yes, sir. Thank you, sir.